Okay, welcome to the second presentation of the data attribution reading group. In our last meeting, we talked about influence functions. Influence functions are designed to approximate the so-called leave one out approach. To briefly recap, suppose we have a cancer prediction task, and we train an image classifier using this training data to predict if the tissue image contains tumor cells or not. And we want to understand the influence of this individual training data points on the model prediction for this particular test image. The leave one out works as following. We first remove one training data point from the dataset, and then retrain the model on the remaining data points. And finally, observe the change of the model predictions. If the change is significant, then that means the removed data point was influential on the original model. And we can do this repeatedly to each of the training data points to measure their influence. This process can also be equivalently viewed as having a 0-1 weight for each of the training loss for each training data point. Removing one data point is equivalent to set the weight to be 0. So we can imagine there's a mapping between the training data weights to the prediction on a test data point. Note that this f function is not the model function, but a rather complicated mapping encapsulating the model retraining process. For leave one out, we will only set one data weight to be 0 and observe the change of the model predictions. So here we are setting the first one to be 0. We can also set the second weight and see the change, and also the third weight. In today's meeting, we'll introduce methods motivated by a different problem, which is counterfactual predictions on a subset of the training data, which means we're going to set multiple data weights to be 0 simultaneously. And then we want to predict how the model prediction changes when we are training on this set of subset. This essentially sets up a slightly different definition of data attribution or the data influence problem. And this leads to the need of new methods and also new ways of evaluating the data attribution methods. The rest of the presentation is based on these references. You can refer back to here if you're interested in learning more details. There are two recent papers that formulated similar versions of this counterfactual prediction problem under different contexts. In one paper, it is called data modeling, while in the other paper, it's called data utility function learning. Here we'll use the first one to formalize this problem. Suppose we have a learning algorithm A that takes a training data set S and returns a model. And we also have a target function F that outputs the outcome of a model returned by A and evaluated at a test data point X. The outcome could be either the test loss or the model prediction logic on this data point X. So this function takes X, the data point X, and the training set S as input, and is also dependent on the learning algorithm A. Now we have some subsets, Si, of the training set S. And we can write the target function F with Si as the input. And this means this target function will output the outcome of the model trained on this subset SI using the learning algorithm A, and still evaluated as a test data point X. Then we can formulate the problem as, can we have a surrogate function G that maps a binary vector to a value that can approximate this F function? Here, the binary vector corresponds to the presence of a data point. Suppose we have D training data points, then the element being 1 indicates the data point is present in the subset, and 0 means the data point is removed. So each of this binary vector correspond to a subset of the training set, SI. And the function G could also be parameterized by some parameter theta. And we assume that we have access to models trained on some data subsets coming from a distribution DS. So G could be learned from the pair of SI and the target function evaluated at SI. So here we are sampling M such subsets, and then we can minimize some loss function between these two to learn the parameter theta of G. Ideally, this surrogate function G should be cheap to evaluate on any binary vector, so we'll be able to easily quantify the influence of the individual training data points. One thing to note here is the test data point X is fixed throughout this problem, and the G function does not depend on this X. So the G function is trying to approximate F evaluated at a fixed X. So that's the reason why we may be able to use a relatively simple G to approximate this very complicated target function F. In the data modeling paper, the authors propose to use a simple linear surrogate function G, which they call a linear data model, to approximate the target function. And to learn this linear function, we will uniformly sample subsets from the training sets with the same size alpha D, where alpha is kind of a number from 0 to 1. That is the proportion of the subset. So like with this, like we'll uniformly sampling subsets with the same size. And finally, with this sample of the subsets, we'll retrain the model on the subsets and get the target function value. And we will learn the linear data model G by minimizing this lasso objective. Well, this seems to be overly simple. The authors conducted extensive experiments to show that this linear function can approximate this counterfactual prediction target function F reasonably well. And here's their experimental setup. The experiments are all done on image classification tasks. They choose the target function in this experiment to be the prediction margin, which is the prediction logic for the correct class minus the highest incorrect class. So when this value is positive, then the model is making a correct prediction. When it's negative, it's making a wrong prediction. And the experiments are based on 2 variants of ResNet models on 2 image datasets, image classification datasets. In this table, the alpha indicates the size of the sampled subsets. and there are 4 settings corresponding to different alpha. And the numbers in this table are the number of models trained on like the sample subsets of this under each setting. So like in this case, it means we'll sample subsets of that is 10% of the whole training set. And one thing to note that is these numbers are not enumerating all the possible subsets with this alpha size. But it does require a large number of samples of subsets and model retrainings to estimate the G function well. Here are the experiment results. In this plot, we first sample some held out subsets that didn't appear when we estimate the G function. And we can train model on this like newly sampled subsets and get the true target function value f evaluated on this newly sampled subsets. So these values will serve as our ground truth. We can also directly make predictions on the subsets with the estimated G function. Then we will compare the predictions using the G function with the ground truth f values. So in this figure, we are specifically having a in-distribution setting, which means that the subsets sampled for evaluation have the same size as the subsets used for estimating the G function. So for example, here alpha equals to 0.2 means when estimating the G function, we're using subsets with 20% of the data. And when we are doing evaluation, we're also using subsets with 20% of the training set. And here, similarly, it's like 50%. So we can see from this figure is the prediction using the G function and the ground truth values align very well. So there's a kind of linear relationship. And if we calculate the Spearman rank correlation between the prediction and the ground truth value, the correlation coefficient is very high. It's as high as 0.99 in both of this case. So this evaluation can be viewed as an extension of the leave one out rank correlation metric, which we introduced in our last meeting for influence function. Now, instead of leave one out sets, we're evaluating on random subsets. The authors also evaluated on some out-of-distribution subsets that have different sizes as the ones used to estimate the G function. In this scatter plot, the points with different colors correspond to different ways to get such out-of-distribution subsets. And here are like several different ways to do it. Overall, well, the Spearman correlation is not as perfect as in distribution, but it's still fairly high. So here on the CFAR dataset is 0.96, and on another dataset is 0.89. So when measuring with the rank correlation, like this linear data model, the linear function generalizes pretty well on both in distribution and out distribution settings. This paper also introduced another way to evaluate the effectiveness on counterfactual prediction, called the prediction brittleness with respect to training data removal. The idea is that if I can do good counterfactual prediction, so I can use it to identify the top influential data points on the model output. And if I remove these data points, they are more likely to flip the model output than removing other data points. And in this evaluation, we do this for a bunch of test data points. And for each test data point, we remove the top influential data points one by one until the model prediction is flipped for this test data point. So in this plot, the x-axis represents the number of training data points being removed, and the y-axis represents the proportion of the test data points that got their prediction flipped by removing a certain number of training data points. For example, here, like it's the 200, right? So it means after removing 200 training data points, about like slightly more than 40% of the test data points we evaluated have their prediction being flipped. So for the data model method, the top influential data points are identified by looking at the theta vector. So recall, like the theta is a vector with length of training data size. So each element of this theta vector corresponds to one training data point. We can identify the top influential data point by just looking at the values, magnitude of this theta elements. So the ones with the largest coefficients in theta will be the top influential data points identified by data model. So the removal will be essentially removing the ones with largest theta value one by one. And the authors also compared the removal guided by data model with some other baselines, such as removal guided by influence function. And in this experiment, data model appears to be the most effective in terms of flipping the prediction. So in this other paper, they similarly aim to feed a parameterized function to approximate the target function, which in their paper they called like data utility function. And they are not using a linear function, but instead a deep set model, which is a neural network model with the input as a set. So they also like sample subsets and retrain models on that, and to get ground truth target function values, and then learn this parameterized deep set G function using that. And they demonstrate that this estimate function can be used to effectively guide active learning. So basically, they show that this learning this kind of target function is also possible by using this deep set model. Another interesting concept introduced in this paper is the utility transferability. So this is about the question, how similar are the target functions or utility functions F for different learning algorithms A? So essentially, if like some training data points are important for one learning algorithm, will they also be important for other learning algorithm? So this is very relevant to the active learning concept. And they also proposed efficient ways to measure the utility transferability. And empirically, they find that the utility function tend to be quite transferable across some common machine learning models. So that indicates that if we learn this target function using one learning algorithm, we sometimes may be able to directly apply that for other learning algorithms. So to briefly summarize, we so far have talked about data attribution as a counterfactual subset prediction problem, which can be viewed as a generalization of the leave-one-out approach. For some target function of practical interest, such as like the test loss or model prediction, we can learn it reasonably well with a parameterized linear model or deep set model. But one caveat is that this learning often requires a large number of random subset sampling and also model retraining on these subsets, which is computationally expensive and not scalable for large applications and models. So our next question comes to, is it possible to efficiently approximate the target functions without the tens of thousands of subset sampling and model retrainings? This study by Park et al. Tells us that it is possible. In this work, the focus is on an additive surrogate function. So this can be viewed as a generalization of the linear data model. Recall that the linear data model function G is written as a free parameter vector theta times the binary vector corresponding to a subset Si. Now, suppose the total number of training data points is n, then this theta will be an n-dimensional vector. Now, in this paper, they assume that there's a tau function that outputs an n-dimensional vector, and the additive surrogate function G will be defined as this tau function, the tau vector times the binary indicator vector corresponding to some subset Si. So here Si is a subset and S is the full training set. And Z is the test data point. So the tau function is essentially a function that measures the importance of each training data point in this training set S to some output evaluated as a test data point Z. And this importance is measured by an n-dimensional vector. So linear data model is apparently a special case of this additive function. Another example is influence function. So we can set tau as like any influence functions, and this will also give us a surrogate counterfactual prediction function, right? By just like have an influence function times this binary vector, then we'll get a counterfactual prediction function on a subset. Now, but the question, of course, is how does this perform, right, in this counterfactual subset prediction task? Note that like for the linear models, we already see that it requires tens of thousands of model retrainings to learn this G function well. But the influence function can be directly calculated based on just one model. So if the influence function can perform well, that will be a much more efficient solution. However, not very surprisingly, the influence functions do not perform very well. We actually already see the comparison between the linear data model and the influence function in terms of this prediction brittleness metric, right? Here is the results when we are evaluating them in terms of this run correlation metric. So these two, the blue and orange boxes, are two variants of inference functions we introduced in our last meeting. And the linear like this green dots in this plots are the linear data model in the previous work we just talked about. So the y-axis is the rank correlation, the higher the better. We can see that in comparison to this linear data models, this influence functions are performing much worse in terms of this rank correlation, right? However, this paper by this Park et al. Shows that it is possible to construct a function similar to the influence functions, and at the same time, it performs well in this task. And they are similar in the sense that instead of like feeding a parametric model using tons of sample subset and retrained models, we can directly derive an analytic influence estimator for the top function, and then to make the counterfactual prediction. And this solution is this TRAK method, which are the black stars here. And we'll introduce the method in a moment. The TRAK method is a little bit complicated, I would say. And also, I think not all its components are thoroughly understood why it's contributes to its superior performance. So I will first just briefly introduce what the TRAK method is without much motivation, and then try to compare it with inference function to give you some high-level insights. For simplicity, let's assume a binary classification case, although it's not hard to generalize to multi-class case. The first thing TRAK does is to linearize the binary classification model. Here, F is the machine learning model, not the target function. And we can view it as a function of data point Z and also the model parameter theta. And we will linearize the model in terms of theta for a fixed data point Z. And this is done by having Taylor expansion at the parameters theta star, which are parameters learned from the full training set. This linearization turns the binary cross entropy loss on a complicated model F to essentially a logistic regression model. In this logistic regression model, the parameters are still theta, which are like the vectorized parameters of the original model F. But the features for this logistic model are not the original feature, but rather this gradient vector. So this GI is the gradient vector of the original model evaluated at data point ZI for like each of the training data points. Then in the second step, so when we have a neural network model, the dimension of the gradient vector GI can be very large. So in the second step, the TRAK method further applies a dimension reduction on the gradient vector GIs by a random projection to improve the computational efficiency. So here, like P is a random matrix and random projection matrix, and then this will reduce the vector to another feature map phi. So this phi will has a much smaller dimension than this GI. And this random projection is a common technique for dimension reduction. Then in the third step, we will apply a variant of influence function on this linearized and dimensionally reduced model to get the influence of all the training data points to form a tau function. So this is a vector of n dimension where n is the number of total training data points. So you may recognize like this the format is pretty similar to some variants of influence functions we talked about in our last meeting. And here like this is very similar to the empirical feature matrix in some influence functions. And finally, there are two more tricks used in the TRAK method. One trick is Ensemble. So instead of estimating the influence using just one model, the TRAK method independently train multiple models, and then estimate the influence on this independent trained models, and then aggregate the influence score to get the final scores. And another trick is sparsity. So basically, the scores are post-processed by soft thresholding to make the small values to be zero. So this is a whole process of the TRAK. My takeaway, my high-level takeaway of this method is that it can be viewed as an influence function plus a few tricks. Specifically, the first step and the third step together can be viewed as a variant of influence function. And what makes this whole method much more effective than influence function is the additional tricks. So basically dimension reduction, ensemble, and sparsity. And furthermore, in their ablation study, the contribution of sparsity is relatively minor. So the most important ones are dimension reduction and ensemble. Now let's revisit their experiment results. Here the x-axis is the computation cost, while the y-axis is the correlation between the counterfactual prediction and the ground truth obtained by actual retraining. Here the TRAK method have like there are results with different computation costs, and these are due to the use of different number of ensemble models in this method. So when we have more ensemble models, then that will lead to higher computation cost. But what people find is that when we are doing this ensemble, we just need tens or hundreds of model ensemble to get performance as high as linear data models trained from tens of thousands of models. So overall TRAK requires orders of magnitude less computation than linear data models, while still achieving very good performance in this counterfactual prediction. Note this x-axis is in logarithm scale, so the difference between these two are quite significant. The authors also evaluated the method in terms of prediction brittleness, which we introduced earlier. And again, we see that the TRAK method with just 100 model ensemble achieves the same performance as data models with 50,000, like data models estimated from 50,000 models, 50,000 models. So it significantly reduces the need of model retrainings and subset sampling in comparison to data models. So how does this kind of ensemble and the dimension reduction contribute to the performance? The author did an ablation study for the effect of these two important tricks. In this plot, first we can look at the different curves. The different curves correspond to different number of ensemble models, from 10 models to 100 models. And the y-axis is again the rank correlation performance. So it's clear that we will have better performance as we increase the number of models in the ensemble. So the contribution of ensemble is pretty clear. The x-axis refers to the dimension reduced by the random projection. So actually, it's the dimension after the random projection. So the like the lower this dimension means the more reduction, the higher the dimension means the less reduction. The dimension reduction was actually motivated just by computational efficiency in the method design. So ideally, when the dimension is larger, where we have less information loss by the projection, the performance should be better. However, in practice, this is not the case. So as you can see, the best performance is obtained somewhere in the middle. And the original dimension without projection is always the worst. The author suspected that this is due to some regularization effect, but the exact reason is still not super clear. So while there might be still some mysteries of this method, but one takeaway is that this method can really, like, without really like learn from the actual retrained models, and without like, instead of like learning from that, but just like forming this kind of analytic expression, we get a method that achieves very similar performance as the linear data model while being much more efficient. For like one more thing I want to mention is that for this TRAK method, the Ensemble, the number of models used in Ensemble is a major factor influencing its computation cost. Like for example here, if we are able to reduce the number of retrained models in the Ensemble, then we'll be able to further improve its computational efficiency. So in actually one of our own recent work, we developed methods that can further improve this Ensemble step. Specifically, we found that we can replace some independent trained models with something that can be obtained more efficiently. One method is to use the dropout masks. Like the idea comes from the fact that like dropout is motivated by efficient way to mimic ensemble, right? So what this method did is, like in this figure, this green points represent a handful of independent trained models from different random initialization. Now, assuming these models are neural network models with dropout layers, we can turn on the dropout masks at test time to obtain several variants of the model with different dropout masks. And so this gives us kind of several different models, and we can ensemble these blue points, which can be obtained very efficiently, instead of having like tens of independent trained models. And it turns out that this kind of ensemble also gives us some improvement in attribution performance. Another method is on large generative models. We can use efficient fine-tuning to replace fully retrained models. For example, here again, the green points are a handful of independent trained model. And on top of that, we can do several LoRa fine-tuning and to obtain some slightly different models in comparison to the original original model. And then we can use this LoRa fine-tuned models in our Ensemble, and that also turns to improve performance. And here's the result. For dropout, like we observe like this dropout Ensemble improves the data attribution performance with very little computation overhead. So in this plot, the x-axis represents the number of independent trained models, while the different curves correspond to different number of dropout masks used in the Ensemble, right? And we can see a clear performance improvement by including this dropout mask variance of models in the Ensemble. And similarly for the LoRa fine-tuning based Ensemble, while the LoRa fine-tuning has will lead to slightly more computation overhead compared to dropout, but its cost is still significantly less than retraining, and it still improves the performance in terms of like this run correlation for attribution. So finally, to summarize the studies introduced in this presentation, we have explored data attribution as a counterfactual subset prediction problem, which can be viewed as a generalization of leave one out, and it arguably makes more sense in some practical applications. While this seems to be a more challenging task, we first saw that we can learn a surrogate function given a large number of samples of subsets and models we train on them. And this surrogate function can be learned to make very good predictions on this counterfactual prediction task. Then we saw that empirically, we can actually construct some inference function style methods with some additional tricks that can also perform reasonably well on this task. And this type of method do not require massive model retrainings and making it much more scalable. So that's about it for today's presentation. See you next week.